Yeah, I'm starting that now.
Yeah, thank you. So good morning, everyone. Welcome to our virtual informal systems seminar. And it's my great pleasure to introduce our speaker today, Mr. Dengwang Tang. Mr. Tang is a PhD student in electrical and computer engineering department at University of Michigan, Ann Arbor. He works with Professor Vijay Subramanian. He received 2 bachelor degrees in 2016. One is in computer engineering from the University of Michigan, Ann Arbor, and the other is in electrical and computer engineering from Shanghai Jiao Tong University, Shanghai, China. He received a Master of Science degree in electrical and computer engineering from University of Michigan in 2018. His research interests include multi-agent dynamic systems, dynamic games, mechanism design, and information design. Today, his talk will be on games among teams with asymmetric information. So without further delay, let's welcome Mr. Dengwang Tang. And Dengwang, the floor is yours.
Yeah, thank you, Shuang, for the introduction. So today I'm going to talk about dynamic games among teams with asymmetric information. And this is joint work with Hamid, with Professor Subramanian, with Professor Nayar, and Professor Tenikatis. So first, let me talk about multi-agent systems. Multi-agent systems can model many engineering and socioeconomic settings. In these systems, multiple agents take actions over time on top of an ever-changing system or environment to achieve their respective objective. And they also have different information for them to make decisions. These systems have a wide range of applications, such as energy systems, edge device computing, and e-commerce platform, just to name a few. For example, in e-commerce platforms, you can think of the sellers are competing with each other, not just in one shot, but over time. So there are mainly 2 different types of multi-agent dynamic system settings, namely teams and games. In a team setting, the agents have aligned interests and they collaborate with each other. In a game setting, the agents in general do not collaborate and they have conflicting objectives. In this talk, what we are going to investigate is a setting where groups of agents collaborate to compete with other groups, so namely games among teams. So why games among teams? So here are 2 potential future applications that motivate our research. The first one is automated vehicles. In the future, we may live in cities where automated vehicles not only dominate the ride-sharing business, but also fundamentally change how we commute and travel. So the vehicles will roam around the city to serve customers, and their decisions are made by algorithms, not a driver. Vehicles from the same company, now fully automated, can collaborate on their strategies in order to serve more customers and make profits. And fleets of vehicles from different companies will compete with each other for customers. So this is one application. Another application we have in mind and another motivation is the Spectrum Collaboration Challenge held by the Defense Advanced Research Projects Agency. This competition encouraged researchers to develop better strategies to utilize spectrum resource in order to deal with the scarcity of spectrum resource. So people are encouraged to develop transceivers work in teams, and teams compete with each other for spectrum resource, and the teams develop joint strategies to sense the spectrum landscape, avoid inference, and exploit opportunities to achieve efficient use of spectrum, and teams compete with each other for spectrum resource. So the other half of the title is information asymmetry. So let me talk about information asymmetry. In many real-world multi-agent dynamic systems, information asymmetry is an inevitable and important aspect. Because of information asymmetry, both games and team problems become much harder due to the need of estimating other agents' information. In general, the information asymmetry will exist among all agents, no matter whether they are in the same team or not. Remember, we are talking about a setting where you have games of teams. So the question is, why cannot the members in the same team just simply communicate with each other to overcome the information asymmetry? Well, there are several reasons why they may not be able to do that. First is physical constraints. Then the communication can have delay, and you need to take action very quick, which means that before the information comes in, you need to make a decision. This results in information asymmetry. And the communication may have a cost, and the team may not want to afford, may not be able to afford that. And finally, also there's possibility of being eavesdropped by other teams like this, which is not good. So the teams may just avoid the communication overall to avoid being eavesdropped by other teams so that they give up their information advantage. So we are dealing with, so the general problems we are dealing with are dynamic games among teams with asymmetric information. Now let me talk about the challenges associated with this problem. So at each time, agent's decision do not only affect the current payoffs, they also affect what agents know in the future. So this is the interdependence of decision and information over time. Next, you have the domain of the strategy is growing over time. As information accumulates. So regarding to this point, in this talk, we will attempt to compress the information of the agents so that their domain of the strategy doesn't grow over time. This will be a repeating theme over and over in this talk. Then you have the problem of dependence of belief on strategies. So because of the asymmetrical information, the agents need to make decisions based on their beliefs, not just their perfect observations, because they don't necessarily have perfect observations. And these beliefs in general can be dependent on the strategies used by other agents and other teams. But you don't know these strategies. So this is another problem. Finally, a problem special to games among teams is a coordination within team problem. You need coordination within teams to achieve team optimality, not just person by person optimality in each team. So in this work, we will address these challenges in the context of a specialized model. So before I jump into existing work, any questions?
It seems that you can proceed, and
Okay.
and people can, if they have questions, you can also post in the chat, so we can stop for questions later on. Yeah.
Sure. Okay, let me proceed. So let me talk about some existing work on dynamic games. Dynamic games, of course, is a huge field and a huge research topic in game theory, in economics. So the economists have been analyzing dynamic games for years. What they mainly focus on is what we call repeated games, where the underlying environment doesn't necessarily change over time. People are just playing repeated game. And what they focus on is analyzing possible payoff profiles. So our focus here is on systems where the underlying environment is changing over time. There has also been considerable amount of work on zero-sum dynamic games, where the special properties of zero-sum games will allow researchers to develop specialized methods. And the rest are non-zero-sum games with underlying dynamic systems. And we would like to mention a few. The first one is Muskin and Tirol's 2001 work, where they introduced the notion of Markov perfect equilibrium in a dynamic game with perfect information. And they conclude that in these systems, agent can base a decision on the Markov state of the system rather than the entire history. So that's a compression of the agent's information. So this is for the perfect observable case. Then you have Nayar, Gupta, Lambor, and Basar in 2013. And under the crucial assumption that the common information-based belief is strategy independent, they are able to derive the results that the agents can make decisions based on compression of common information. And they also develop a sequential decomposition procedure to determine such equilibrium. So this assumption eliminates one of the challenges of the dynamic games, that is, the belief can be dependent on strategy. When the belief is not dependent on strategy, you can do something about it. And the next work deals with a case where the belief is actually dependent on strategy. And this work is the most similar to ours, except this work concerns with games of individual players, and we consider games of teams. And their result is a sequential decomposition procedure to determine compression-based equilibrium. We will come back to this work later when we introduce the details of our work. So let me, without further ado, let's introduce our model. Any questions? No. So in order to address the fundamental difficulties of dynamic games instead of technical problems, we consider finite horizon game of finitely many teams, and where each team has finitely many members. The members in teams will be denoted by tuples, where the first entry is the team number and the second entry is the member number. At each time t, each agent, ij, takes an action, which we denote by the letter u of t, ij. And team I has a vector value dynamical system where each component corresponds to a member of the team. We assume that each team system is a controlled Markov chain controlled by the actions of all the members of all teams. So not just this team controlling this team. All the actions will have an effect on this system. The evolution of different team systems, though, they are conditionally independent given the actions. So in terms of what each agent knows, we assume that the actions of the agents are publicly observable to all agents of all teams. And in addition to that, there are also noisy observations of each team's system, which we denoted by Y. And the distribution of these observations are also affected by the actions of the teams. So, yeah. So both the actions and the noisy observations at time t will only be available to the agents only after they take action at time t. So it will be available at time t plus 1. In addition to that, each agent ij can observe their own component of their team's dynamic system perfectly with 0 delay. And within the same team, the agents communicate this perfect observation of their states with a delay of d. So as you can see, there's also asymmetric information within the team. And after this, we assume that all the initial states, control noises, and observation noises are mutually independent primitive random variables with non-distribution. And we also assume that all agents have full knowledge of the model we just described, including the distribution of random variables and these functions and the description of the model. So we are in the classical stochastic control setting, not the reinforcement learning setting. And we also assume that all the random variables we introduce here are finite values, so that we can avoid as much technical problems as possible. So to summarize, there are 3 levels of information in our model. The first level is a common information known by every member in every team that is given by noisy observation and all the actions. The second level is the information that is private to team I. This part is consisted of the perfect observation of their states up to time t minus d. Recall that d is an internal communication delay. And the third level is information that is only private to a specific agent, which is per component of the state after time t minus d. So let me describe the strategy a team uses. A pure strategy of a team is a collection of functions that each members use at each time to map their information into actions. And a mixed strategy is simply a distribution over pure strategies of a team. Note that we allow this distribution to be any distribution, which means that the strategy choices of members of the same team can be correlated. Also notice that we follow the game theory tradition to assume that different teams will use independent strategies. So strategies can be correlated within team, but they are independent across teams. So what is the objective of each team? So each team wants to maximize their total reward. And the reward is given by the expected value of the sum of instantaneous reward. And if the agents are using mixed strategies, then the reward under mixed strategy is simply the average of the rewards under a pure strategy. So after formulating this, since we are dealing with a game problem, we have to specify which equilibrium concepts that we are using. In this work, we are going to use the simplest concept, which is mixed strategy Bayes and Nash equilibrium of the teams. A mixed strategy profile is team Bayes and Nash equilibrium, TBNE, if each team cannot unilaterally deviate to other mixed strategy profiles to strictly improve its utility. Note that a unilateral deviation here means that possibly multiple members in one team decides to use some other strategies. So not just one agent, but one team. So in this work, we have 2 objectives. First, to address the challenge of increasing domain of strategies, we would like to characterize a subclass of team Bayes and Nash equilibrium where the agents can compress their information. And to address the interdependence of decision and information over time, we would like to develop a sequential decomposition procedure to decompose the game into sub-problems so that we have the hope to determine such an equilibrium. So before we jump into our results, let's have an overview of our results.
Sorry, Dengwang, could I ask a question on the previous slide? So are you not assuming there is some form of sequential rationality?
True. Here in this problem, we are because of the challenges of the problem, we are first considering the simplest equilibrium concept.
But wouldn't it be the case that since your end objective is to get some form of sequential decomposition, in sequential decomposition, we would only be able to find, I mean, sequential decomposition in some sense automatically removes equilibria where players are making non-credible threats.
Yeah, that will happen. So,
okay.
Yeah, in fact, in our paper, we show that if you apply what we do in this paper, what you will get is something stronger than just Nash equilibrium.
Okay.
Yeah, but for time being, for the purpose of making the proof simpler and for the illustration simpler, we just deal with Nash equilibrium at first.
Okay.
Yeah, sure.
Thanks.
It's a good question. So let me overview our results. The first step we are going to take is to transform the games among teams into a game among individual players, where the individual players are called coordinators. And so then we will solve the game among coordinators. The game among coordinators will be a dynamic game with asymmetric information. And these coordinators will have some information in common and some information of their own, which are called private information. So doing this transformation allows us to simplify the problem by taking advantage of the fact that there is significant amount of common information among teammates. So this is the first step we take. Then we solve this lifted problem. In this lifted problem, we introduce a subclass of strategies where coordinators can compress their private information. And we will show that equilibria exist in this subclass. And finally, we introduce a subclass of strategies where the coordinator compress both their common information and their private information. In this case, we were able to develop a sequential decomposition procedure to determine those equilibria if this sequential decomposition procedure succeeds in finding a solution. However, we will also address the problem that since we compress too much, we have equilibria loss in the situation. Equilibria may not exist in this subclass in all games. So there's a contrast between the two compressions. So any questions to this point before I jump into the steps? Sure, I'll move forward. So the first step is to transform a team into an individual player. How do we do that? We will follow the coordinators approach introduced by Nayar, Mahajan, and Tanakatis in 2013. The idea is shown through the following example of a two-person team. So the members of this team will have some information in common here. This is in green. And they also have their respective private information in blue. The idea is to introduce another decision maker called the coordinator into the team as follows. The coordinator will know the common information and only the common information, not the private information. The coordinator then, instead of taking actions herself, they assign what we call prescriptions to the agents on how they should map their private information into actions. So the prescription can be think of as a full table that describes the action to take under all possible realizations of private information. And what the agent do in this case is they receive the prescription, they do a table lookup, and they find the corresponding action to take. So by introducing this new decision maker and taking this point of view, the members of a team are no longer individualistic decision makers with free will, rather they are part of the system. And now we can view the system as a hyper system being controlled by the coordinator, where the coordinator's actions are prescriptions. So first, let me note that this transformation is equivalent to the original problem. This transformation does not bring more strategies to a team, even if we introduce one more decision maker. This is since the coordinator is a fictitious construct, and the coordinator only knows the common information. So any agent can play the role of the coordinator herself. So at the same time, this transformation is not restrictive, because any team strategy, regular team strategy, can be conceived as a coordinator strategy. So now we have completed the transformation. Let me introduce some new notations. So the coordinator is now the decision maker, the single decision maker for this team. We call the coordinator of team I, coordinator I. So coordinator I's action at time t is a prescription, which we will denote as gamma t of I. And the coordinator can play mixed strategies, just like a team can play mixed strategies. But here, since this is a single decision maker with full recall following standard game theory results, we can equivalently consider behavioral strategies, which we call behavioral coordination strategies. Then, which means that the coordinator chooses randomized prescriptions based on the common information, which is coordinator's information, along with the past prescriptions. So now we have described the strategies of a coordinator. And then we can just analyze coordinator's Bayesian-Nash equilibrium in behavioral coordination strategy instead of analyzing team Bayesian-Nash equilibrium. So we have completed this transformation into a game among coordinators. The game among coordinators is a dynamic game with asymmetric information. And let me just describe its information hierarchy. The first level is what all the coordinators know. That is the noisy observations and action up to time t-1. Then each coordinator has some additional information, which contains the system state up to time t-d and the past prescriptions up to t-1. And after this transformation, no coordinator would have any knowledge about the states after time t-d. So in the rest of the presentation, we will refer to the common information of the coordinator as simply the common information, the private information of coordinator as simply the private information, and the states after time t-d as the hidden states. So we have completed this step. However, the game among coordinators, while being a game of individuals, is still a complicated problem, because we still have the challenge that the information is growing with time, and the actions and the information are interdependent over time. And we also have the challenge that actions are hidden, because coordinators assign prescriptions. Prescriptions are hidden to other coordinators by nature. Because of this reason, that the actions are hidden, and many other reasons, the results of Ouyang, Tawafogi, and Tanakasis in 2016 does not directly apply to the game of coordinators, even if there are some similarities. So in the next, we will attempt to solve the game of coordinators and answer the following questions. So, do there exist equilibria where coordinators can compress their information? And can we develop a sequential decomposition procedure to find such equilibria? So the next step is step 1. So before that, any questions for the first step? Okay, good. So yeah, step 1, compression of private information. Recall that the coordinator i's private information at time t is given by the states up to time t minus d, and the prescriptions up to time t minus 1. However, we will show that coordinator I only need to use what we call the sufficient private information, Si of t given by the last perfectly observed states and the partially realized prescriptions. So what are the partially realized prescriptions? In a short sentence, they are the d minus 1 most recent prescriptions evaluated at the current information of the coordinator. So the idea is that you assign some prescriptions in the past, but now at today, you have some new information, which means that you can plug in some variables that you know now to the old prescriptions. So the partially realized prescription is a summarization of how the hidden states were mapped into actions in the past, provided what is known now. Some examples are given by the following. When d equals 1, the delay is 1, then PRP is empty by definition, since the coordinator knows all the past states. Coordinator knows xt minus 1. There's nothing hidden to him. And for d equals to 2, the coordinator will know the state at time t minus 2, but does not know the state at t minus 1. So in the previous stage, the coordinator assigned the prescription to ask the members to map xt minus 2 to t minus 1 to some action. Now the coordinator knows xt minus 2, but the coordinator still doesn't know xt minus 1. So the coordinator then need to retain a part of this prescriptions, which relates to how xt minus 1 was mapped to action, given the knowledge that xt minus 2 is plus 1 in this case. And the coordinator doesn't need to use the other half of the table because the other half was not used in this system, and the coordinator knows that. So we will refer to such strategies as sufficient private information-based strategies. So these are the strategies that uses the common information and sufficient private information instead of common information and full private information to choose randomized prescriptions. So these strategies are simpler to implement than generic behavioral coordination strategies for the following reason. The size of the sufficient private information does not grow with time. And the sufficient private information can be sequentially updated as new information comes in, meaning that you can compute st plus 1 with s of t. So you don't have to compute it with the whole information. You can sequentially update it as new information comes in. So here comes to our main result in this step. That is, there exists equilibria where all coordinators use such strategies. So before I talk about the proof idea, let me just give a remark. In game theory, existence of equilibria is typically established under assumption of full recall, meaning that the agent knows what he knew before. But however, using a SPIB strategy means giving up full recall. At time t, you use st of I and you forget st minus 1 of I. So this is describes the significance of the theorem. So let me talk about the ideas on how this is proved. First, we restrict attention to epsilon trembling strategies of coordinators. This is for technical reasons. What are epsilon trembling strategies? They are strategies where all prescriptions will have some probability of being realized. And this probability is at least epsilon. Then we show that if we fix all other coordinators strategies and look at coordinators i's problem, this decision problem can be thought of as a Markov decision process, where the common information and the sufficient private information as a tuple forms a state of this MDP. Based on this observation, we then define a best response correspondence following the game theory tradition. But the best response correspondence is defined using the sequential decomposition of this MDP, not just any best response of coordinator I. So this step allows us to deal with the fact that SPIB strategy doesn't have full recall. If we just define the most generic best response correspondence, we will not be able to prove the theorem. Then, using Kakutani's fixed point theorem, you can argue the existence of epsilon trembling SPIB strategy-based equilibrium. Finally, you take the limit as epsilon goes to 0 to argue that the theorem holds. So this is step 1. Any questions?
So you made a remark that in this case, the sufficient private information is not accumulated over time. Isn't it the case that at least part of it becomes part of the common information?
Yes. Well, not really, because the part of it becomes just Markov. Just the team can forget that because they have new perfect observations. Yeah.
So the difficulty is really throwing away the prescription part of it compared to the standard argument?
Yeah, the prescription
part. The partially evaluated prescriptions.
This is one thing that we do. The difficulty is that you don't have full recall, which means that at time t, you know Si of t, but you do not have access to S t minus 1. You forget that. You choose to forget that. And in game theory, if you want to talk about existence in general, full recall is something that they usually assume.
No, so I'm just wondering if I could have made it part of the common information at first, and later on you can say, since the part of the state is known, I can throw the past while looking at the problem from the point of view of common information.
That's that's a good trick. Yeah, but that part deals with the control problem of a single agent. Here, in terms of the existence problem, it's a little bit more delicate.
Okay, I see.
Than that. Yeah.
Okay, thanks.
So let me continue with step 2. So now we have completed step 1 to compress the private information. The next step is to compress common information. And recall that the coordinators information is consisted of the following: the noisy observations up to time t minus 1, actions up to t minus 1, all the local states up to t minus d, and all prescriptions up to t minus 1. We have compressed the private half of it, but the common half is still growing with time, as you can see. So how can we compress that part? And also keep in mind that we have this goal of sequential decomposition. So how can we do the compression of common information and sequential decomposition at the same time? So the idea, a possible way to do it is to compress the common information into what we call common information-based belief. This is similar to POM-DP, where you compress the action and observation history into a belief on the state. Here, you compress the common information into a belief on the private information and the state. So this was done in both decentralized control settings and dynamic games. And in both settings, sequential decomposition procedures were developed based on this information state. So to apply this idea in our game where we have already compressed the private information, the idea in our game will be to compress the common information into the common information-based belief on sufficient private information and hidden states, or the joint probability distribution of SPI and hidden states given HT of 0. So this is the idea. This is a crude idea, but using special property of our model, it can be shown that this belief can be expressed as a function of the following quantities. The first group of quantities is the beliefs on each individual sufficient private information, which is the probability distribution on each individual SPI of each individual coordinator rather than the joint distribution. And then the second group of quantities are the uncompressed values of last D-1 noisy observation and last D actions. So these if we have these quantities, then we can compute the joint belief. So then we have this refined idea of compressing the common information into all these quantities over here, rather than this joint belief. So, however, we still have the problem because the belief of SPI based on common information are strategy dependent. So the simple way to see that is that in the common information you have some actions, and these actions may signal what the private states of other coordinators are, but you can only understand that signal by knowing their strategy. This belief can be sequentially computed with Bayes' rule at each time t, but this Bayes' rule, the form of this Bayes' rule will depend on the strategy profile of all the coordinators. Therefore, unlike the compression of private information into SPI, there's no fixed way to compute this compression of the common information, which means that in this subproblem, we have to determine the compression of common information and the strategies at the same time, rather than in the private information case, we can just have an ad hoc compression of the private information, and that will always work in all cases. So let me describe what strategies we are looking at. So we are looking at compressed information-based strategies. So in those strategies, it will be described by two parts. The first part is a belief generation system, which is a collection of belief update functions. And these functions defines how coordinator I sequentially updates the beliefs from the common information. Then the second part is a belief-based strategy, which defines how the coordinator I, after compressing the common information into beliefs, how they map those beliefs to the prescriptions. So a diagram will be like this. So there are two compressions applied. The compression of common information is done with the belief generation system, and the compression of private information is done as we have described in step 1. And after both steps are done, you choose a prescription based on the compression rather than the whole information. So these are the type of strategies that we consider. Note that this strategy forms a subclass of SPIB strategies. We are not just interested in any CIB strategies. We are interested in those with reasonable belief generation systems. Because here, as we have described, this belief generation system can be anything, but we want it to mimic what is reasonable. Following the similar concept in Ouyang, Tavafogi, and Tanikatis, we focus on a subclass of equilibria where all the coordinators play CIB strategies with the same belief generation system. And the beliefs they form are required to be consistent with the strategies according to Bayes' rule. Recall that those beliefs are essentially strategy dependent, and here, because of we don't know strategy, we use this belief generation function to generate those beliefs. But at the end of the day, we want these generation systems to reflect objective reality. So we want it to be consistent with the strategies under Bayes' rule. So this gives us a subclass of strategies. Why is this subclass desirable? We can look at the two conditions that it says. If we have the same compressed common information, if we have the same belief generation system, then by definition, all coordinator will have the same compressed common information. This allows consensus to happen. And if the third condition holds, then the common information-based beliefs, as I have just described, they will reflect objective reality. So this is a nice subclass of equilibria where the coordinators compress their information into beliefs, and those beliefs are true beliefs. They reflect the objective reality, and the coordinators choose their actions based on those beliefs instead of the whole common information. So this is the subclass we are shooting for. So the nice thing about this subclass is that it also suggests a sequential decomposition procedure. It works as follows. Because we have the same update rule and consistent update rule, the compressed common information at time t can be seen as a consensus summary of the past that is agreed by all coordinators. So it can be used to derive objective beliefs on the states and information at or after time t. So think of this situation where all the coordinators are now at time t. They want to decide what to do for this half of the game, starting from time t, given that what they have already done before. This part can be seen as a new game, starting at time 0, that is parametrized by this consensus summary of the past, B of t. We call this game G greater than t, or parameter B of t. And this is true for t, this is true for t plus 1, which suggests that we can go backwards in time to start from the last time period to solve the game for the last time period, and then the one before, and the one before, and so on. And at each time, we only need to solve a specific stage problem rather than the entire interdependence of information over time. So how does this work? So suppose that we have already known the interim expected payoff to go at equilibrium for the game in time t plus 1 for every realization of the CCI compressed common information B of t plus 1. And this information is given by the value functions. Then for the coordinators need to choose some strategies at time t given that they already know that what is the equilibrium that will happen from t plus 1 going on. This is like in POM-DP where you already solved the subproblem of t plus 1 from so on, and then at the stage t, you solve a stage optimization problem. So here the stage problem is the follows. First, we have two parts. One is recall that we have two parts of the strategies. One part is how do you use the belief to map it to that prescriptions. The other part is how do you compute the belief. First, let's just fix the second part, which is how we compute the belief. Fix this part and then allow coordinators to use any way to use this belief, but fix how they compute this belief. If we fix that, then we get a stage game that is described as follows, where the coordinator have some private information, that is sufficient private information. The coordinator selects a prescription, and the coordinator has some utility that can be expressed as a function of the CCI, the SPI, and the prescription. So if you restrict the belief update rule to be some update rule psi t of star, then you have this nice stage problem. Then if we can find the equilibrium strategy profile in the above stage problem, and it happens that this equilibrium strategy profile is consistent with the belief update rule under Bayes' rule, then we have find the equilibrium for the game starting from time t. Why is that? Yeah. So this part is it's a bit technical, so bear with me. So if we look at this stage game, so we have restricted the coordinator to use update rule, but the coordinator doesn't have to be restricted, right? They can use any strategies they want. If we restrict them to use a rule and we find the equilibrium in this game, this means that the coordinator I is using the best CIB strategy that he can use to respond. But is this best CIB strategy necessarily the best strategy that he can respond to other players? It turns out that under the conditions that we have given for CIB, CBNE, that is here, it is actually true. So if all the other coordinators are already using the same belief update rule, and this update rule is consistent with strategies, then as coordinator I, you can use this same belief update rule, and you can use a CIB strategy to respond without loss of optimality. The idea of the proof of this lemma is control theoretic, basically fixing all other coordinator strategies, and then lets the coordinator use this belief generation rule. Then this belief generation rule will contain the true belief of other coordinators SPI, and the coordinator I can use this belief, and you can actually prove that the coordinator I faces an MDP with the state given by BT and SI of T. So let me wrap around this again. So suppose that we have solved the game problem at t plus 1. Then we want to solve it at time t. How do we do that? We don't just solve a game, we solve a stage problem. This stage problem is made up of two intertwined parts. One is the stage game. Another part is the consistency requirement. We want to find a pair of strategy and belief update rule such that the strategy will be an equilibrium given the update rule, and the update rule will be consistent given the strategy. So it's kind of a fixed point equation situation. But this is restricted to one stage. if we can solve this problem, then we can go from t+1 to t. And this is exactly the idea of this whole theorem, where if we start from the last time period and starting from the value function that is 0, and we solve this intertwined stage problem backwards in time for each t, then we obtain a coordinators Nash equilibrium. However, the bad news is that this sequential decomposition procedure does not always have a solution. The reason is that the intertwined problem of each stage does not always have a solution. You may end up in a case where at some stage there's no solution. But if this procedure works, it will give you an equilibrium. And in the paper, we don't have the time to deal with it here. In the paper, we identify 2 instances where this procedure is guaranteed to work. So lastly, I want to mention the existence problem as I have promised. So in the compression of common information part, you will end up with non-existence problem. As we have mentioned here, this sequential decomposition doesn't necessarily have a solution. In fact, this whole equilibrium concept may not always exist in all games. And you can use a textbook like signaling game example, just filling it with different numbers to show it. And I don't have the time for the details of this, but this example is an instance of our model. And in the paper, we use a variant of this example to show the non-existence of CBN. And let me conclude. I'm pretty much on time. So let me conclude. So dynamic games among teams with asymmetric information has many applications. And we transform games among teams to game of individuals with the coordinators approach. We develop a general approach to characterize a subset of Nash equilibria with the following feature. That is, at each time, each agent can make their decision based on compressed version of their information. And we have 2 subclasses, one where we only compress private information, and the other one which we compress both common and private information. In the first subclass, equilibria always exist. In the second subclass, equilibria doesn't always exist, but the second class has the advantage that it admits a backwards inductive sequential procedure to solve for the equilibrium if the procedure succeeds. So some future work of this work includes considering a broader class of compressed information-based strategies, because we have existence problem in compressed information-based strategies. If we make the class larger, we may be able to avoid this problem. Another direction is concerned with applying approximation methods for games among teams. For example, if we are content with epsilon equilibrium instead of equilibrium, maybe we have some methods to deal with that to approximately compress the information. The third problem is deals with reinforcement learning in games among teams, where the agents does not necessarily know the parameters of this whole game, and they need to learn this along the way while playing this game. So this is all the talk. Merci à tous. Thank you.